So, once you get on to the 4A worksheet, we start seeing things that require a knowledge of normal force, F normal, and force of tension. This is the only disagreement I have with the sequencing in your book. We don't introduce these until, I think, 4B, but we kind of need them now. So both of these come from the idea of opposing forces, force pairs, equal and opposite forces. So if you have a surface, you're going to be talking about normal force. And the first two on the worksheet are actually normal force problems. So and then we'll talk about force of tension and moment. So we'll stick that there. All right, so if you have a surface that you are exerting a force down on, the surface is exerting a force back upwards on you, that's normal force. So here's our guy in the first problem. There he is. I think he's holding, a giant pumpkin above his head or something? Well, it's a pumpkin now, so don't tell me. Okay. He and that pumpkin are a system, and he and that pumpkin are exerting a force down on the surface because the force of gravity is pushing them down into that surface. So we have Fg. But if he is not sinking through the surface, then the surface must be exerting an equal force upward on him. And that would be F sub n, normal force. Now, we're on a flat surface. Normal force is going to be equal to the force of gravity if you're not sinking through the surface, or if you're not rising up into the air. If the surface is holding, they're going to have to be equal. But, and we will talk momentarily about what happens on a slanted surface. That's a little bit different. In general, normal force is going to be overall in opposition to gravity. But there are going to be situations where it's not equal to gravity. So with that, can you set up number 1? Okay, I'm going to pause this. You try setting up number 1. So what is the force of gravity equal to? Well, the force of gravity is equal to the mass of whatever it is times g, which is acceleration due to gravity. What's the value of g? 9.81 meters per second squared. Okay? So if I ask you what's the force of gravity on your body, it's your mass in kilograms times 9.81 meters per second squared. That gives you newtons, because kilograms times meters per second squared. Does that help? Yeah. Okay. Note that in this problem, we're not talking about any lateral forces. There's no force to the right or the left. Note that it's also on his feet. Well, the force of gravity is the force downward. The normal force is the force upward on his feet. You're looking for normal force here. Force of gravity is... Now, how do we know that they're equal? So in this case, and here, I have heard it said that the single best predictor of success in physics is doing proofs in geometry. And I had a high school geometry teacher who never made us do a single proof. And I struggled mightily in physics.
We did a million proofs.
Good. You are well set up for success, my friend. Because what we're doing here is saying, well, the sum of forces on the y-axis is equal to what? The question you have to ask yourself in every situation, is this object or individual rising up into the air? No. Is this object or individual sinking through the platform? No. Therefore, sum of forces on the y is 0. Because they're not accelerating in either direction. So sum of forces on the y is equal to ma, but it's equal to 0 at this point because there's no acceleration. Well, it's also equal to all the forces up minus all the forces down. Does that make sense? Okay. So that's how you're proving that. Everybody stand up. It's okay. It's a really simple pose.
Oh boy.
Oh boy. Okay, the yoga pose we're going to do is called mountain pose. I'm going to pause the recording. If
I noticed it in the shower.
the things that go through your head in the shower. If you are looking at a problem where they're asking for the force up on each foot, if it's evenly distributed, which we're assuming, then that's going to be half of the force on both feet. Does that make sense? Perfect.
Wouldn't it just be the pressure?
Is about force of tension. If there is no surface, but there's a rope or a cable, that's where we're talking force of tension. I'm going to pause this. You guys go ahead and do 1 and 2. When we have something hanging on a rope, on a cable, that's when we see force of tension. So if we have an object here, and instead of sitting on a surface, yes, you all saw the password, it doesn't matter. It's my daughter's birthday.
Actually, we did. Actually, we
Huh?
can't see it.
Oh.
Actually, it blocked it out.
Oh, did it? Okay, cool. Well, if you figure it out, you can wish her a happy birthday. So if we have an object that is suspended on a cable, there's no surface to exert a force back upward on it. So now we're in a situation where we have force of gravity, but we can't have normal force, but yet this thing isn't sinking and it's not rising. So now, in place of force of tension, or in place of normal force, our opposing force is what we call force of tension. It's the tension on the line. And just like, so I can get rid of my little cable here, just like with direct contact forces, it doesn't have to be directly on an axis. You can have a force of tension that is split over 2 axes and you have to resolve it. So we could have a box on the floor with, I'm making all my cables purple today, I don't know why. We could have a cable there that's being pulled on where the cable is, 40 degrees above the horizontal. Well, that looks like 400, sorry. 40 degrees above the horizontal. We would have our force of tension, we would have force of tension X, we would have force of tension Y. Same exact process you use to resolve any other vector. We can have multiple cables on an object where we have, yeah, exactly. And when you get down to the bottom of this page, we're going to start hanging things from the ceiling. No, not literally, but in the problems. We could hang things from the ceiling. I can get out the force board and we'll hang some things.
I remember when Mr. Klein opened
Oh,
the
yes, I've heard wonderful stories about lifting people to the ceiling and
That
stuff.
was weird.
Yeah.
It's fun.
Did you get the science behind it?
Yeah.
Okay, good. Good.
I didn't have Mr. Flag. What was going on there?
All kinds of wildness.
Pulled ourselves up into the ceiling.
Wildness. Okay, questions on normal force versus force of tension. I have a brief little tutorial I recorded years ago. I'll put it up there, so if you need to dip back into that, you can. I have to go find it on my YouTube channel. But that should get you through these problems. When you get to number 5, before you start crying, before you turn to self-destructive behavior, because it's ugly, it asks you to do a proof to figure out the angles. Honestly, I probably can't do it cold. I have to go back to my notes, because I've done it repeatedly, but it's ugly. So what I want you to do is focus on getting it solved to a point where if you had the angle, everything would be good. And then we'll try getting you through the angle, and that's the least of our concerns, and it's a fun brain teaser. Okay.